Okay class, it's time for an example using sine and cosine. So behind me right now I have an example for you of a counterclockwise rotation of 50 degrees from our original starting position. This is our original starting position, and this time you'll see that the radius is equal to 1 unit. We call that a unit circle, 1 unit. That 1 unit could be anything, centimeters, meters, kilometers, you decide, but right now it's 1 unit. Which means this original starting position, instead of being at R0, is at 1, 0. And we're going to rotate around counterclockwise. Well, as we rotate, we realize that the r times the cosine of theta and r times the sine theta is the position both horizontally and vertically around the circle can be given by the coordinates cosine of 50. Note, I didn't say 1 times cosine of 50 because 1 times cosine of 50 is still cosine of 50. So this is cosine of 50, and then the y value is just sine of 50. Or 1 sine 50 again, but multiplying by 1 doesn't change things. We don't include the 1 in the front, it's just sine of 50. I included an approximation to 3 decimal places on top of those as well, 0.643 and 0.766. So these are approximations. Well, you might approach a problem like this and say, how can I use the given information to find perhaps 3 or more other positions around this circle? Well, the great thing about this is the symmetry of the circle helps us to find those. So I drew in blue over here a triangle that looks to be almost the same as that triangle. By almost the same meaning it's a similar or it's a congruent triangle. What I'm going to do is kind of help you with this a little bit and say that this too is 50 degrees. Well, if I want to know what this position was, x and y coordinates, I would have to put in my x and y are these x and y coordinates using the angle of rotation from our initial position. If I know this is 50 degrees, to get from here rotated out to there would be to rotate this amount of angle measure. Well, that's the same as coming from 180 all the way halfway around the circle here, back 50. So this is 180 degrees minus 50. This would be 130 degree rotation. So if I wanted to make these calculations complete, I would write something like the radius cosine of 130. But the radius is 1, so I'm just going to write cosine of 130. And then the sine of 130 here. Well, I could then pull out my calculator and figure out what those values are, but here's the glory of this. I already know those coordinates, and if these are supposedly the same triangles, check it out. This would have to have the same y value. So the same sine of 50, or the same value for sine of 50, 0.766, is the same value here for sine of 30. So this too is 0.766. And the y value has to have the same dimension of the same component here, or the x value, excuse me, has to have the same component, the horizontal component. This must be the same length of 0.643, but you have to note something. It's in the negative direction. So it's to the left. So this would be a negative 0.643 on the coordinate grid. Okay, so that might be one way you see the data. But there's more we could do. What if we then said, let's rotate 50 degrees beyond the 180 mark? What if we came down here to create a triangle that was also 50 degrees here, thus making this angle 180 degrees plus 50. Okay, your 230 degree mark, I would know these coordinates without having to actually calculate the cosine of 230 and the sine of 230. I could fill in these values based on what I know. The x value has to be a negative 0.643. The y value has to be now a negative 0.766 because of the symmetry of the circle. One more rotation would put us over here with another 50 degree mark. This time the 50 degrees is down from this direction. So if I imagine going all the way around the circle counterclockwise would be 360 degrees, but I'm pulling back 50 of those. So I'm subtracting 50 to give me 310 degrees. So this coordinate would have to be cosine of 310, sine of 310. But before I calculate, I'm just going to use my same symmetry ideas. This is now a positive x value equivalent to that piece, 0.643. But the y value down here is negative at the same height this one was, at the same component length that those were, but now negative 0.766. Well, that's pretty neat how we can do that with the symmetry of the circle. We could even go one step further and say, okay, if this is 50 degrees, this side of the triangle must be a 40 degree mark, we could draw in the other triangle at a 40-degree rotation and do the same thing. It would swap the x and y values around. All right? We'll get more into that in class.